Hello, everyone. Thank you for coming and listening to my talk. Today, I will be discussing my paper on assessing local fit in CFA models by approximating probabilities. So just a little bit of an overview. So I'm going to first kind of discuss a little bit about CFA models and their uses, and a little bit of the kind of method and approach to how and why fit assessment is needed in these types of factor models. And then I'll describe my approach, and then I'll be applying it to a data set I simulated, and then I'll discuss some of the implications and directions that this research is going. Okay, so confirmatory factor analysis, or CFA, is pretty commonly used in test construction, and it's used as a way of working towards finding validity evidence, specifically construct-related validity evidence, when we're trying to measure difficult to directly observe constructs such as like self-esteem or math ability or different personality characteristics. And so in a lot of these types of scales, there are subscales or subcomponents of the overall construct we're interested in. And so it becomes like a very multidimensional set of items, and what we want to do with CFA is to map on a statistical model onto that multidimensional set of items so that we can basically find evidence that we are measuring, at least in the structure of what we are wanting to. And so what this project is helping in this evaluation of this measurement construction. And so suppose we start with a very simple scale where there's only 8 items. And so underneath these 8 items, we're actually going to say there are these 4 we think are actually going to be in one factor, and these 4 are in the second. And it could end up being something like this. So we have these 4 over here and the 4 over here. And so what we hypothesize going into it is that we have this very nice simple structure of each factor is only measured by 4 items, but the 2 factors are correlated. And so that gives us a very simple interpretation of what each item is measuring and how the items and factors or different subdomains of the construct we're interested in are related to each other. However, this is typically not the first thing that we encounter. We'll probably start with doing something like EFA, where we'll get something that looks like this, where we have 2 factors and they're correlated, but all items load up all factors, and we're trying to figure out, well, that's not very parsimonious, so what do we need to do in order to possibly eliminate some of these paths, or maybe we need to add something in order to kind of more parsimoniously represent the 8 items. So we could get down to something like this from statistical evidence in some way, where we have only factor 1 has 2 cross-loaded, or items 5 and 6 are cross-loaded on factor 1 and 2. And so this becomes a little bit more difficult to interpret, because what are item 5 and 6 really measuring? And so another way that this could, another possible factor structure is having residual covariances, into where the basically relationship between item 5 and 6 onto factor 1 comes from items 2 and 3. And so it's a little bit simpler factor structure in terms of the measurement of the different items, but now we're trying to deal with residual covariances, and that's just difficult to interpret sometimes. And the difficult part is justifying what these pieces are. And so what do we do in order to make those justifications? So we do that by assessing model fit. And so in one way is global model fit, where we really just look at the relationships between the observed covariance structure and the model implied covariance structure, or the expected based on the model. And so we want to basically look at the differences between those, and that is global fit assessment. And so there's a ton of different methods that have been developed for that, such as the chi-square test of model fit, paired fit index, RMSEA, SRMR, a whole host of other ones. But in general, all of these fall under this category of global fit assessment, where the general consensus is that we are not able to really capture fine-grained information about why a model may not fit a given set of data, or where misfit might be occurring. And so that is where we go to something called local fit assessment. Local fit is where we try to get at individual relationships between items. So how do the relationship between item 1 and 2, how do we capture that based on a model? So for local fit assessment, it's really geared toward this idea of how do we make modifications about these different relationships. And so do we need to add or subtract different paths or covariances in order to help increase fit? So different ways of trying to approach modifying our model are modification indices, fault tests, likelihood ratio tests, and instrumental variables. And so each of these different approaches have a shortcomings, and they're all they have similarities as well. And so one of the difficulties, especially with methods such as modification indices, which are very common, is that they often give contradictory information about what changes need to be made. So that is kind of what we want to start to avoid. And so that is the main goal of the new method that I'm proposing, which I call the region of practical equivalence probability approximation, or the rote probability approximation. And so what we want to do here is we want to essentially approximate the probability that the parameter estimate is outside of the rope, or outside the region of practically equivalent. And so equivalent in this case will be 0, because if it's 0, we don't really care about it very much. And so the whole goal of it is to provide an interpretable metric, a probability, in order to help us understand the parameter space of our model. And so the logic is to evaluate what the probability is that a parameter is outside the region of the parameter space that we deem is not does not help us interpret the factor structure in any new way. And so we do this pretty commonly in exploratory factor analysis, where we look at factor loadings and say, if it's below 0.3, it's probably not very informative of that factor, and so we say an item that low of a loading isn't important, and we basically move it to 0. And so what the probability approximation is we try to figure out what's the probability that that doesn't occur. So what's the probability that it is greater than 3? Or what's the probability that we do care about the magnitude of that parameter? So think of it kind of like this. Say we have factor loading. What we want to do is say, given that this is the range of all possible values of factor loadings that it could take on, what's the probability that it is greater than 0.3? So what is essentially this area over here? So we're trying to get at what that area is by using different approximations, or doing a approximation. And so we can kind of express this more mathematically by this simple probability statement of what's the probability that the parameter is greater than or equal to some value given our data. And so if we're talking about loadings, we can say it's 0.3. If we're talking about error variances, we could say it's like 0.25 or 0.1 or whatever we as researchers deem as the lower bound or upper bound of what we want to say is not influential in our decision making about the structure of the factor model. And so we estimate this by basically going into a Bayesian framework, and we kind of sidestep a lot of the computational issues by utilizing Laplace's method. So Laplace's method is just a second-order Taylor series approximation. It looks scary down here, but it's very, very simple because it's just a couple derivatives, and it allows us to very easily kind of estimate some of the more complex posterior distributions that can occur in Bayes methods. And so what we want to do is we want to see if our method of trying to come up with these approximate probabilities of whether different parameters are really, is it helpful in identifying these non-zero paths in a factor model. And so what we want to then compare it to is the sampling distribution. So the sampling distribution gives us information about how accurate the probability is. So if we can basically get at the sampling distribution we arrive at through the rope approximation method, whether that is very similar to the sampling distribution under like the true model, if those two empirical and the true sampling distributions match up, then we have evidence that we're going to really do well at estimating these probabilities. So to basically start, what I did was I took a random sample of 300 from this population, which is taken from Boland's book and one of his more recent papers, to try to get at just a simple three-factor model, nothing too complicated. And what we're going to do is we're going to take out these two error covariances when we estimate the model to see if we get evidence of misfit, which we will, because we know we did. And then we will see if we can recover these unestimated paths using the rope probability approximation. Again, we want to see if that probability is very high, getting these different paths. So basically I just used Levon and R when I estimated the misspecified model. No shocker, it does not fit the data. And so we need to figure out why does the model not fit the data. And so using the rope probability approximation, we want to try to identify a potential modification that might help us understand where this misfit is occurring and potentially why it's occurring. And so what we get is basically the list over here is all the parameters that could possibly be non-zero, and we want to essentially what's the probability that that parameter is greater than either 0.25 for a covariance / correlation or 0.3 if it is a factor loop. So now, interestingly, these two right here are the two that we kind of identified as being, or those are the two parameters that were in the data generating model. The error covariance between item 7 and 4 and 3 and 2. Those have the highest probability. So I included the factor loading down here because it is the factor loading between factor 1 and item 9 was the highest factor loading or highest probability found for a factor loading. Now, basically what this tells me is that the issue is very likely to be in one of the error covariances and not a factor loading, because so many of the error covariances have a much higher probability of being outside that rope that we care about. So, and when looking at the sampling distributions for the item 2 and 3 error covariance, we got a pretty big difference between them, indicating that we are not estimating that probability well in this case. However, for item 4 and 7, we did a very good job of estimating that sampling distribution. So it's a very intriguing finding that we might actually do well under some circumstances of estimating the probability. And so in general, it's a very, very quick method, which is great, and a very interpretable approach to assessing model modification. And so what we want to do is, in more work to understand how this method will be applied in future datasets. And so thank you, and you can see the rest of the paper on the OS stuff. Thank you.